Is it going to work? This is a perfectly reasonable question to have during a new project. But it's not one I often wonder about as I'm making something for the first time. Usually, all the engineering efforts that I put into a design have me pretty sure of the outcome, whether that's out of confidence in my decisions or just plain ignorance. But every once in a while, I design something that I'm not 100% sure will actually do what I want it to. So I go into the build knowing I may have to make some adjustments on the fly, or do a complete redesign, or in an absolute worst case, abandon the idea altogether. This is one of those builds. I have a new design that I want to try out, and I don't know if it's actually going to work. But if it does, it'll be pretty cool and really, really useful. Alright, what is this mysterious and possibly questionable design that I want to make? Well, I recently built this awesome vice-mountable rotary fixture plate for making rounding part corners a breeze. And so far this thing has exceeded my expectations. No, seriously, this thing is absolutely dialed. But I still need, yes need, a set of guides for locating parts that don't necessarily have corner holes in them. There are 3 requirements for these guides. They need to be adjustable in position, they need to be solid when locking them down, and most important of all, they need to always be perfectly square. And I mean perfectly. If I can measure so much as 1/1000th of an inch of variation across the edge, I won't be pleased. Simple enough, right? Well, as the old adage goes, the devil is in the details. I can't just whip up a set of bars and T-nuts to slide into this groove, because even if I manage to keep the clearances as minimal as possible to allow things to slide, these will still be sources of error. And over time, that error will only increase as everything wears. Unacceptable. I need something that can have both adjustable clearance and wear compensation, but also be self-squaring. So here's what I came up with. The heart of it all is the dovetail slide. Think of it like a T-nut, only it's meant for a dovetail slot. The top has a set of chamfers that will match another set of chamfers on the bottom side of the guide bar. This keeps the guide square to the slide. So the guide mounts to the slide that rides in the groove. You with me? Now things get a little tricky. I also need the slide to stay square in the groove. I could try to work it out so that the top chamfer locks with the guide bar at the same time that the slide engages with the dovetail groove. But even if I manage to get this distance correct to 1/10,000th of an inch, one is always going to touch before the other and nothing will get tight. So I'm going to need a little bit of the secret sauce. Compliance. By slitting the dovetail slide down the middle, I can make it a flexible piece. And including a V-groove creates a set of ramps that a semicircular nut can ride along. Now, as I tighten the screw from the top, the guide bar locks and squares to the dovetail slide first. Then, as I tighten further, the nut is pulled into the V-groove, which expands the slide, pulling it down further into the dovetail groove while squaring it as well. Makes sense, right? Yeah, it does to me too. But the more I look at it, the less I feel that way. I can already spot a few things I'm not so sure about. But at some point, you have to stop pondering the possibilities and just start on a functional prototype. Yeah, that's what I'll call it. Then I have an excuse if it doesn't work. Okay, let's begin. I'll need the guide bars in order to make the dovetail slides, so I'll start on these first. And I've got an inappropriately sized block of A2 tool steel that will do the trick. Don't worry, I have a plan. I'll start on the top, fly cutting it flat and square to the mill. Then switch to a 4-flute end mill to work on the perimeter. First the left side, which I'll set as a reference, then move over to the right, cutting this down to establish the length of the bars. I'll repeat this on the front and back as well, making this wide enough for both the bars plus the width of an end mill to fit between the two. Now to cut away the middle. This is effectively a slotting operation, and my preference would be to use a 2-fluted slot mill. These are better for slotting operations because by only having 2 flutes, you only ever have 1 flute engaged at a time, so tool deflection is minimized, making a more accurate cut. But it turns out the longest 2-fluter I have isn't long enough, so I'll have to stick with the 4-flute I already have mounted. This is perfectly acceptable though, since I don't have to take this slot to an accurate width in a single pass. I left enough room in here to come back after most of the material is removed to clean up each side independently and take the guide bars to width. And pretty much just like that, I have 5 out of 6 sides on 2 parts squared up and ready to go. I ended up turning a little more metal into chips than if I had cut 2 individual bars and milled each side square one at a time, but for the time this approach just saved me, this was a no-brainer. These could technically be either the tops or bottoms of the bars, so I think I'll go ahead and call them the bottoms and work on the chamfered grooves. Not that I couldn't dial it in later, but this will pretty much guarantee that the groove comes out perfectly parallel to the sides of the bars. An absolute must if I want everything to be square later on. I'll start by cutting away the square portion of the grooves that will give clearance for the chamfering operation. Dimensions aren't critical here, but it never hurts to practice precision even when it doesn't matter. Now for those chamfers. I've got this chamfering bit here to do the job, and it has a very subtle but important feature that I have to consider. The bottom is flat rather than coming to a point. I have to take this into account when referencing this cut, otherwise I could overshoot the width of the chamfers. So after a little bit of figuring, I get the cutter in position and send it on its way. I'm not going to worry about measuring it though. 1, because I can't think of a reliable way to do so in this setup, and 2, because I'll be able to account for any small deviations when I make the next part. After a little deburring, these are looking great. Now to free these from the rest of the stock and work on the other sides. Since I'm already set up here, I'll go ahead and just use the slitting saw for this. Hey, wait, the coolant stopped. Don't! Ugh. Okay, Brandon, what's the #1 rule of coolant? It only helps if it's actually present. Now your perfectly good slitting blade is toast. Let's try this again with a fresh blade, and this time I want to see that thing drenched. And there goes another blade. This is the point where both past and present Brandons learn the hard way what the A in A2 tool steel stands for. Air. Meaning this is air hardening tool steel. Meaning that flash of red we saw, then it immediately air cooling, basically heat treated the area around the cut to a hardness somewhere in the neighborhood of 62 Rockwell C. The high-speed steel blades I'm using are only about 63 Rockwell C. So pretty much those blades were never getting through that hardened area. Learn from my mistakes, people. Luckily, I wisened up and moved over to the bandsaw to cut the parts from the stock. Of course, avoiding that hardened area from the first attempt. Alright, with that lesson learned, let's finish out these guide bars. I'll get these mounted up in the vise and start milling them down to thickness. I still have that hardened area to contend with, but since I'm using a carbide face mill with hardness around 70 Rockwell C, cutting through this is not an issue. After getting within a few thou of the final thickness, I'll switch to a fly cutter to take it the rest of the way while also achieving a better surface finish. Nice. Now to round these out with the screw slots. I'll get the first bar mounted against a vise stop and use an edge finder to set my reference on that corner. Then bring in the drill and pop an undersized starting hole at each end of the slot. And since I have a vise stop in place, I can swap to the other bar and repeat the operations on here as well while I have the tool mounted. For these slots, I will actually use a 2-fluted slotting mill, starting with the wider counterbore portion of the slot. So I'll plunge this all the way to depth, then let this thing churn its way across the part. On second thought, that might have been a touch too aggressive. Looks like the massive cutting forces on the spiral flutes of the end mill actually pulled the end mill down slightly, overshooting the depth. On top of that, I also got quite a bit of cutter deflection, which I wasn't expecting since I used a 2-flute mill. You can see a step in there from the return pass. Thinking on this now though, the deep cut combined with the spiral geometry of the flutes meant the end mill was cutting on both flutes at once, causing the deflection. I guess this is one of those nuanced things you never really think about until it happens, but you can guarantee it's ingrained in my memory now. Fortunately for me, the depth and width of this groove is pretty arbitrary, so I'll bring the mill back in to even out the bottom, and might as well open up the slot a bit to clean up the sides. Much better. I'll repeat this on the second bar, taking it to the same dimensions just so everything matches. Then I'll also bring in a 1/4 inch end mill to cut the through slot in the bottom. Looking sharp, but not in a good way. Just one more thing and these are finished. Much better. Dropping some nice consistent chamfers on a part always makes such a big difference. Of course, now that these parts are finished, it occurred to me a way to check the width of these bevels, so let's have a look. Placing a pin against the bottom and side of the groove, I can bring in a depth micrometer and measure the distance from the side of the pin to the side of the part. By my math, this should be an even 12 thousandths. But I'm reading closer to 22. Not sure where I went wrong earlier, maybe I forgot to offset one of the axes or something. I can of course account for this when I make its mating part, but now that I know this error is here, it's going to bug me until I fix it. So it's back to the vise for some quick skims along those bevels to open them up closer to my target. Alright, now these are finished. It may have taken a few lapses in judgment to get here, but we made it. Barely. I can move on to making the dovetail slides next, but I think I'll need to do some testing to nail the final fitment. So instead, I'll whip up the half-round nuts next. Don't worry, I'll make this a quickie. Who doesn't love a quickie, am I right? The nuts are round, so naturally I'll start on the lathe. I've got a piece of A2 tool steel perfect for this. It even has a center drilled end, so I can move right on to turning down the length. I'll need enough for 2 nuts, plus a little extra for work holding. And after nailing the diameter, I'll part this off. Already halfway there. I told you this would be fast. On the mill, I'll set this up in a collet block with about an inch sticking out. After squaring up the end with an end mill, I'll get a touch on the top side, then mill away half the rod to make the semicircular shape. From here, I'll use the edge finder to locate the center line and end of the rod, then start the sequence adding the threaded hole. After hacking this off and repeating that once more, I have 2 nuts almost ready to go. Just a quick trip back to the vise to clean up the last ends. Well, this is a first. The vise stop is thicker than the part, so nothing gets tight. Oh, something just dawned on me. My grandfather had this second vise stop here that looks like he modified it to be shorter. I never pieced together why, until now. There we go. Now I can finish these parts out, milling the first to length, then swapping for the second and repeating on it as well. I'll also go ahead and give these a good deburring and a little love on the emery board. Nice. That takes care of the top guide bars and the bottom nuts. Now it's time to work on the piece that goes in between, the dovetail slides. I've got another hunk of A2 tool steel for this as well. So I'll get this mounted and quickly square up the top and sides just like the guide bars. Only this time, once I get it dialed in, I'll flip it over and repeat on the bottom as well. I promise, there's a reason for this, just hang tight. Now with all 6 sides square, I'll actually begin sculpting the parts. Yes, parts with an S. I'm making both of the dovetail slides at the same time. I'll start by milling down the front and back to define the width, which is a nice round 16.668 millimeters. Or 21/32 if you prefer obsolete units like me. Now for something less pedestrian. Let's cut the dovetail features. I'll zero the cutter on the top surface, bring the material up to prescribed distance, get a touch on the side of the part, then start taking 20 thou passes along the length. Let's check the progress. I'll use another pin to measure this depth. It took a little bit to work out, but the distance from the outside of the pin to the opposite side of the part should be 0.704 inches. 5 thou to go. One more pass should do it. Perfect. From here, it's just rinse and repeat on the opposite side. This is shaping up nicely. Next are the through holes for each of the clamping screws. Though no need to go all the way through this block, only the part thickness. The last thing I can do from this angle is cut the V-groove in the bottom. A perfect job for the chamfering bit. I'm pretty sure I'm getting my money's worth out of this tool in this project. To measure the depth, I'll use another gauge pin, but first I need to determine a baseline distance from the top. So I'll place a 1, 2, 3 block in here and get this baseline, then bring in a pin and measure to the top of that. I should get a difference of 0.203 and be reading 0.635, so another 32 thou to go. And there we go. Now remember how I went through all that trouble to square up all sides of the block? Well, I did this because now I can turn this in the vise and be reasonably sure that it's square to the rest of the dovetail features I already cut. So next I'll drop a 16th inch hole in the end. This will act as a termination point for the parting slit, so I don't end up with any sharp interior corners that would act as stress concentrations. This tiny drill isn't long enough to go through the whole thing though, so I've got this vise stop in place that lets me flip this and drill the other side without having to relocate the part. Another change of position and it's time for that secret sauce. Yeah, I guess I don't know where I was going with this. Let's cut the parting slit. Lucky for me, the only way I have to do this is with that slitting saw. I've had some time to really reflect on what went wrong before though, so I think as long as I keep this thing absolutely drenched in coolant from the start, I should be alright. Whew. Okay, that seems to be doing the trick. My theory about the air hardening of the steel must be true. Though maybe I went slightly overboard with the coolant. At any rate, it worked, and I also managed to get the slit perfectly centered on that hole like I wanted. Doesn't get much better than that. Next is to mill down the width below the dovetail faces. So I'll get this repositioned with a vise stop, then bring in a roughing mill to hog away the rest of the material on either side. Alright, this is the first time I get to see if this is actually going to fit. Sweet. 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 I still have to nail down some dimensions on the top side, but so far this seems to be perfect. Let's get this freed from the base block and finish up the other side. And with my confidence restored, I'll give the slitting saw another go. Whee! Alright, this part just got a lot smaller. And a lot harder to hold. I can't just clamp this in the vise or I would compress the slit and it would likely come loose. So I guess it's time to come up with a fixture plate of some sort. Okay, I need this fixture to do a few things, and the first is to hold my part perfectly straight while I mill the top down to thickness. I've included a threaded hole on the far end giving me a spot to mount a hold down clamp, so now I can bring in a mill and skim the top surface. Well, half of it anyway. Once I get the first side spot on, I'll flip the part end for end and mill the other side as well. And that's as much as I can do with this as a single part. So over on the bandsaw, I'll cut this into two. Now to pretty up these faces a bit and get them on par with the rest. I'll get the first remounted in the fixture plate, but there's definitely no room to get a clamp in here now. So I'll use a socket head screw to secure it, and then bring in an end mill to clean up the other side and also take it the length. With both of these to size, I can now do the final operation of chamfering the top side. These chamfers are what engage with the groove on the bottom of the guide bar, keeping everything perfectly square. And I can pretty much count on this being true since this fixture plate had its alignment pocket cut in situ. The chamfers also need to be symmetrical side to side to keep the through hole aligned. So I'll flip the part on the fixture and bring the cutter in the exact same distance. Okay, I left a little meat on here so that I can fine tune the clearances, so let's see where we're at. Stacking the slide on the guide, the distance from the top to the bottom should be 0.969 inches. But adding 5 thou-ish for mechanism clearance should put me at, okay, 0.976. Maybe I didn't leave as much meat on here as I thought. Talk about cutting it close. Well, I guess that means I'm ready for a test. Oh, just one more thing though. I'll need to shorten this screw. Okay, now let's try this. Booyah, baby! Excuse me. Booyah, baby. It works. It actually freaking works. I think I absolutely nailed the clearances too. With the screw loose, I can move the guide in both directions. But if I snug it just a bit, that locks the side to side while still letting me move up and down. Then snugging a bit further, and that direction gets pinned down as well. And with the friction between everything, this isn't going anywhere. But what's probably the coolest of all is that this is all done with a single screw. 2 directions of adjustment plus squareness alignment, and it's all done with one frickin' screw. I think this might be one of my proudest moments. I do have one small nitpicky thing to address though. The screw is wrecking the bottom of this slot. But this isn't something a couple of soft brass washers couldn't rectify. Oh, and I guess I'll need slightly longer screws now. Turns out that little mishap making this slot deeper was more of a happy accident. Now there's just enough room for the washer and screw head to hide below the surface. I also went ahead and finished up the other dovetail slide, so now things are truly done. And man, it is such a satisfying feeling to see how well this mechanism actually works. If I want a guide here, boom, locked. Or if I want it here, boom, locked. And with hardly any tightening of the screw, I might add. This is just awesome. But I made these guides for a reason, so let's get this on the mill and play with it a bit. I adjusted the tram of this fixture plate in my last video with this screw, so it should be interesting to see if remounting caused any variation. Well, I'd say that's still pretty much spot on. Same at the 90-degree position as well. Did I mention how pleased I am with this thing as a whole? Let's go ahead and check the guides while we're here. Nice, only 5 thou variation. Wait, no, that's awful. What the fuck? Okay, so I think I found the problem. 2 problems actually. And one is so painfully obvious now that it's stupid that I didn't see it before. When I tighten the screw, the chamfers that align the bar square also cause it to expand. In this case 5 thou or more. So pretty much the straight side needed for aligning parts isn't straight at all. The problem is non-existent on the ends where the bar has more support structure, but that defeats the purpose of this being adjustable. The second problem is more subtle, so let me demonstrate. With the mechanism about 50% tight, you can see I can still pivot the guide bar slightly one direction or the other. Tightening it further and it starts to pull itself towards 0, which would be square, but it doesn't quite get there. And the same happens from the other direction as well. But once it's tight, it doesn't go any further. I'm 90% sure this is a result of the friction between the top plate and the guide bar, and tightening the screws further only increases that friction. So basically the friction I thought was playing to my advantage in this design is a big reason for its failure. Go figure. I'm already thinking of ways to redesign this mechanism to get it to work like I want. But as it stands, that's beyond the scope of this build. Plus I'm going to have to sit on this for a while until I have an epiphany. But even though it isn't exactly to my standards, it still sort of works. It would be a shame to make it this far and not at least try it out. So let's do that. The whole point of these guides was to locate parts for corner rounding. Parts with corner holes can be located with a central pin, but parts without a hole need something else. After finding the center of the table with a coaxial indicator, I'll offset a gauge pin or end mill a specific distance to establish the radius of the round I want. Then bring the guide in, bump it against the mill, and lock it down. After repeating this on the other guide as well, I can mount my part, then clamp it down, and start cutting the corner round. You know, I guess this does actually do what I wanted it to, just not as accurately as I'd hoped. In fact, I'm still pretty stoked that this expanding dovetail mechanism works as well as it does. Sure, it still has some bugs to work out, but this is like a 99% functional concept. I think that qualifies as a win. The whole purpose of this build was to see if a new idea I had would even work. And even though it kind of didn't, it also kind of did. So it's given me a starting point that I can tweak and fine-tune until I get a design that works flawlessly. Designing, machining, and heck, even life in general isn't about getting it right the first time. It's about having an idea and trying it out. Because if we don't try, how will we ever know what's possible? As always, thanks for watching, and see you next time.